Okay, so today we're going to be talking about P300 theory and also analysis, and I'll be talking about both the theory of analysis and then we'll actually go through and analyze some of the data we recorded yesterday. Before we get started, though, I would like everybody to, if you haven't already, please install MATLAB and the EEG Lab toolbox or just the precompiled version of EEG Lab. You can do this sort of while I'm talking about the beginning stuff. It can take some time for things to install and download and stuff. So just get started on this, and then hopefully by the time we get to the actual analysis, everyone has it ready to go. Um, just show of hands. Does anybody have it installed already? One of those options. Okay, most of us. So hopefully it doesn't take too long. And when we take our first break from these slides, anybody who's having troubles, I can go and we can try to figure out what's going on. Seems like most of you have Macs, so maybe Mac users can help each other out because I suck at Macs. But okay, yeah. Any questions before we get started with covering things, or any questions from yesterday that someone was just dying to ask that I didn't cover or anything? All right. So I'm gonna start off with some bad news first, but hopefully the good news of today will make up for it. So I'm going to make this our last meeting, so I'm canceling next week. And the reason for this is just taking too much of my time. And I don't fall for the sunken cost fallacy. So yeah, I'm not going to continue this boot camp next week, but I do plan on continuing this sort of trend of collecting data in these rooms. And since you guys are all trained to do that, if you're interested in practicing data collection during the fall quarter, I plan on actually getting SONA subjects in, and I'll need people to help collect data. So if you're interested, send me an email, and I'd be happy to have you guys on as research assistants, essentially. All I've looked at all of the data that we recorded yesterday, and it is really, really good. I'm really impressed with how quickly you guys were able to get trained and collect that data. So each and every one of you has a gold star, and I'd love to keep doing research with you. So just email me. And yeah, I'm sorry that I just don't have I have too many things to do before the quarter starts, so I need at least this week to do some stuff. Um, but yes, email me if you're interested, and feel free to just email me questions you guys have as you think about this material and revisit it and stuff. I'm here to help, and I really appreciate you guys' time, and hopefully this was a useful experience. All right. So I'm going to give you guys a really brief history of the P300. If you want to know more about this, I can point you to a lot of papers, but also I have an entire lecture about this on YouTube from when I taught COGS 189, and I go in detail into these studies in particular, but I'm going to just take these three studies, highlight a couple things about them, and then I'll go more onto the properties of the P300 that are relative to modern researchers. I'll also give credit to Marta Kudis, who gave me some slides many, many years ago from when she used to teach a class about ERPs, and I essentially everything she has is perfect. So I just took that and tried to summarize it for for this audience. But yeah, so the first study that really found something that seemed to be related to a P300 was Chapman and Bragdon way back in 1964. Although most people, when they're talking about the history of the P300, they do not reference this paper. The only person I've ever seen who talks about this paper is Marta, but she's also very, very thorough and was like doing this type of research at the time, so she knows. But most researchers, they start with Sutton et al., 1965. But Chapman and Bragdon had a really interesting experiment. What they had was they would show they had two different types of stimuli. They had stimuli that were numbers, and they had stimuli that were just bright flashes of light. And on both of those stimuli, they would change the intensity of them, so essentially the brightness. And the participants had a task, and the task was to determine. So they were showing two numbers back to back, and their goal was to determine which number was smaller and which one was larger. So you'd sort of see like a number, a bright light, another number, a bright light, and your main task was just to see which of these two numbers was bigger. Interestingly enough, when you showed people both of the stimuli, you'd see the really early perceptual ERP components, so like the N1 and the P2, And you'll get this from any sufficiently large physical stimulus. It could be a light flash, it could be an auditory beep or a tick, it could be touching your fingertips or something. You'll get these early perceptual components with all of these. So both the numbers and the lights generated those, but only the numbers elicited this large positive waveform about 300 milliseconds after they were shown. And it didn't seem to matter whether or not those numbers were in the dimmest state or in the brightest state. They were all eliciting this 300 milliseconds potential. So what they found, to summarize, is that certain ERPs or components seem to be meaningful, seem to be related to meaningful stimuli versus non-meaningful stimuli, right? So in this case, the numbers were relevant to the task, but the lights were not. And so there seemed to be this thing where, like, okay, the task relevant stimuli are generating this thing. And they also showed that the physical properties of the stimulus don't necessarily affect all ERP components. So before this, it was sort of an open question. I mean, ERP research was very young at this point, but before then it was sort of an open question of what generates certain ERP potentials. We knew about the N1 and the P2 because those are elicited by all sorts of stuff, but this is going the first dive into these cognitive processes and trying to figure out, okay, which of these components are eliciting things that are happening in our brain as a response to us sort of doing the math and churning things versus just raw inputs. So a year after that, Sutton et al. Showed that they had a guessing task for this one, and the task was really simple. But at this time, uncertainty was huge. Everyone was studying uncertainty because they thought that uncertainty was sort of the cornerstone of information and gaining information and parsing information. So they designed a guessing task where participants would see a pre-stimulus and then they would see an actual stimulus. And there were two different types of trials. On some of them, the pre-stimulus would tell you exactly what that stimulus was going to be. So, like, let's say it was, the pre-stimulus was an A, and then your stimulus was an A. I don't think it was that simple, but let's just say that it gave you 100% certainty of what that stimulus was going to be. And on some other trials, that pre-stimulus was ambiguous, so you had to make a guess as to what the stimulus after was going to be. And I think participants actually verbally made a guess. And what Sutton et al. Found was that when you looked at the activity of the stimulus when there was certainty, you wouldn't see that much activity beyond just the physical stuff. But on the task version where you would have uncertainty, you would see this 300 millisecond peak afterwards. And so at this point, people were starting to develop this theory of the P300 that it was reflecting something to do with the resolution of uncertainty and uncertainty processing. So to summarize, they found a positive going component 300 milliseconds that seemed to be related to uncertainty, because again, we were only seeing it in the uncertain stimuli case. It was not affected by modality because they repeated this experiment using both auditory and visual stimuli, so you're getting this component with either one. And it seemed that, so I use this language because of my BCI class, but it seemed that it was the mental characteristic of the stimulus, not the physical characteristic of the stimulus that was generating this potential. So we'd call this an endogenous response rather than an exogenous response. And the component seems to be sensitive to probability. So in the scenarios where there was I think in this particular experiment, there was a higher percent chance of the guess being correct or not. I don't remember the complete details for this experiment, but I'm just trying to summarize all the bullet points. But it seemed to be sensitive to probability, so how likely it was for that stimulus to have been shown in the first place. And the component was also larger on incorrect versus correct guesses. So if you guessed, if you had an ambiguous stimulus and you said, oh, it's going to be an A, and it wasn't A, then that would actually generate a smaller P300 than if you got that wrong. And the reasons for that are somewhat complicated, but it's at least what they found in 65. Now in 67, they were really trying to figure out, okay, let's see if this is really reflecting uncertainty processing. So they had this super cool task, and actually I saved the figure for this one because it's really cool. They had a task where the participants were going to be listening to clicks, and they would either be presented with 1 click or 2 clicks. And the 2 clicks came in 2 different variations. The variations were that it would be shown either 100 milliseconds from the first click or 500 milliseconds after the first click. And what they found was that when you look at the ERP locked to the first click only, regardless of the second click playing or not, if you were in the scenario where if you were in the task where there was a 100 millisecond delay, even if you didn't hear that second click, you would get a P300 approximately. You'd see it 300 milliseconds after when that second click should have played, regardless if the click played or not. And the same exact thing was true with the case of the 500 millisecond delay. So when you had the 500 millisecond delay, you would have, you'd hear the first click, you'd wait 500 milliseconds, and then 300 milliseconds after that, you'd see a P300. And they did a very interesting test of this where the stimuli could be either 100 or 500 milliseconds delayed, and in either case, you would only get the P300 500 milliseconds because that's sort of the maximum or the minimum amount of time you need to process whether or not the stimulus was going to happen, right? So it's like the first click happened, okay, 100 milliseconds happened. I didn't hear the second click, but it could still happen, with this longer delay. And after that happens or doesn't happen, you still get this P300 response. So they showed that, first of all, no stimulus is even required to elicit the P300. It's something that is obviously related to your cognitive processing of the task characteristics. And they also essentially confirmed in this that the P300 latency seems to indicate when uncertainty was resolved, right? So if you were running this type of experiment, without even knowing which condition a certain stimulus was, you could see what the delay was from the first stimulus to the P300 component, and you could tell that, okay, this person was waiting for the 500 millisecond versus 100 millisecond delay. So these are sort of the cornerstones for laying out what exactly the P3 is doing. Obviously, there's, as I was talking with Shawnee yesterday, it's almost definitely the most studied ERP component. I mean, there's definitely the most cited, at least. People use this for everything. It's the largest ERP component, so it's very easy to elicit. It's very easy to utilize as a control signal with BCIs, for example. So there's an insane body of literature on this component. It'd be impossible you could actually spend an entire quarter just talking about the P3, I'm pretty sure, like, if not multiple quarters. But I'll talk about the way that it's studied most often, which is in the oddball paradigm, which is the task that we ran yesterday. So a brief summary of this is that in the 2 stimulus oddball, you're going to have a target and a non-target. In this case, we're going to say that our O is our non-target or standard or background. People talk about it with all of these words. And your X is your target stimulus. And the participant typically has a task, which is either to count how many times they see their X's, or you can have a purely passive one where people are just looking at it. But the task that you give people sort of determines whether or not they're going to elicit the P300 or how big it's going to be. So it's modulated by task constraints. But in the standard 2 stimulus oddball, where you tell them to count the X, although it's not necessarily required, you'll see a much larger positive spike, about 300 milliseconds after the onset of that stimulus compared to the non-target. In reality, with modern synchronization techniques, we typically see the P300 closer to peaking at 400 milliseconds with visual tasks, although it tends to be a little faster with the auditory versions, just because auditory processing is much faster than visual processing. But I think in other sensory modalities, you can get it. It's always within this range of around 300 to 400 milliseconds in young, healthy people. It can be affected by age and different disorders. Sometimes this latency is pushed back significantly. Sometimes it's, attenuated by age and all sorts of stuff. So it has a lot of parameterization to it. And some of the most important things are probability. So this is, when we're talking about the P300, probability should be the very first thing you think of with what affects the amplitude. So if the target is more rare, the P300 amplitude increases. So for example, in this case where we have, only one row of X's, we're going to have a much larger P3 than we would in this case where we have 3 rows of X's compared to the O's. The temporal probability is also very important. So the more time there is between your targets, the larger the P300 amplitude will be. Eventually, I think there is some global maximum of how long you could wait. So it's like if I showed you a target now versus in 1 year, it's probably not going to be too different than like now and 1 minute from now. I don't actually know what that upper limit is, but people usually study it in the, 5-second range to slightly smaller. Yeah.
Real quick, does the P300 spike happen after target? It's like after they see target?
Yes. Yeah. Yes. Sorry, I couldn't have made that more clear. But yeah, so you'll see the P300 about 300 to 400 milliseconds after you see the target stimulus. And in reality, I think this figure shows it well. You'll also typically get a P300 response on average from your non-target stimuli as well. It's just considerably smaller. And you can design your experiment to sort of make this more or less of a problem, but you will usually see this P300 response in both scenarios. But it's typically very, very obvious which one is your target versus your non-target on average. Again, at the single trial level, you typically don't see anything in the non-targets, but as you average out tons and tons of trials. So I'll address this. I didn't have a slide for this, but a problem that you can think of with how many non-targets there are versus targets is that your non-target signals are going to be they're going to have much more statistical power than your targets, right? So you have tons and tons and tons of trials of non-targets. So as you average those together, you're going to be able to smooth out a lot more of the noise and see what the underlying signal is much easier than you will with the targets because they're so infrequent, they're so rare. But even then, even though they're so rare, they still generate such a prominent peak that it's trivial to tell apart targets and non-targets. And some of the first BCIs and stuff, you could get, the very first P300 speller, you could get 100% accuracy using an average of only 5 responses. So all you need is 5 instances of seeing your target, and you average that, and with 100% accuracy, you can say for sure these were the target stimuli versus the non-target stimuli. So it's a very, very powerful, very, very potent and large component. So yeah, the temporal probability affects it. More delay equals bigger P300. So really, really rapid tasks will have a slightly smaller P3. Luckily, especially in our use case of BCIs, it's so potent that you can still go pretty fast, like 500 millisecond delay or less, and still get really, really potent P3s. But an interesting fact is that this is true even if you have a one stimulus task where there are only targets. So you'll play a target stimulus and then just have time. Play a target stimulus, just have time. And since they're still so rare within the time span of empty space, you'll elicit this P300 component. And again, the more frequent they are, the smaller the amplitude. The local probability is also important. So if the previous stimulus was a target, the subsequent target will have a smaller amplitude. So in this case, you'll have 3 non-targets, target, and then another target. This second target is going to have a much smaller amplitude on average from the other targets, but also it's going to definitely have a smaller amplitude than the target right before it. So typically you'll have a larger amplitude if you have something like this. So this tends to cancel out the effect. So if you have non-target, non-target, target, non-target, target, both of these targets will be about the same amplitude, and actually sometimes this second one will be larger than the previous one. What's up?
What if it's a symbol that they weren't expecting to pop up?
So that is a really, really good question. So let me make sure I understand your example. So when you say a symbol that they weren't expecting, so let's say you had 00x04, something like that, right? And the participant wasn't instructed about that. You have just invented the 3 stimulus oddball task, which elicits so I don't know if I have a slide on this just for the sake of brevity, but the P300 is actually a family of components. It doesn't refer to just a single component. And when we're talking about the oddball P300, we typically call it the P3B. So pretty soon after I go through these slides, I'm just going to be calling it a P3B. What you just described, that random stimulus, will elicit what's known as a P3A. So this usually happens when you see an infrequent non-target related stimulus. And what's interesting about the P3A is even though it has different task constraints, it also shows up earlier than the P3B and also in a different part of the scalp. So the P3B is usually maximal around the central parietal regions, like electrode PZ. That's when we'll see it the largest. And again, it's going to be around 400 milliseconds peak. The P3A is more maximal at frontal channels around FZ, and it's going to peak much earlier, around 250 to 300 milliseconds. So yeah, very good job on proposing a study that is a thing.
But then I was going to say, like, part of that is like, it's like the issue of like prepping this as a task, right? There's like constraints to what you can, right? Like,
Yeah.
you can just like surprise them with something that they had no clue was going to come.
Well, you can, and that's how you can get the P3A. So like if you literally tell people you're just going to be seeing X's and O's, and like you just show them a 4 randomly,
That's not like an invalidation.
that's not an invalidation. I mean, if that's what you're trying to study, which people do and have done, and it just turns out that that has a unique effect. In general, so this is a little bit of a tangent, but in general, whenever you're doing some sort of psychological experiment, you get approval from a board, from IRB and stuff. So as long as you're staying within these domains of, you first of all, you're not going to be harming the subject in any way, and you'll also inform them about what happened after data collection if you're going to lie to them or manipulate them in some way, again, that the board determines is not harmful. You have a lot of creativity, actually. I mean, scientific experiments, I hope that I highlighted with the initial 3 that we talked about. They can be really, really like pretty genius and creative works of art, So yeah, you could totally give participants a task and then like have them play something that does not match that at all. And you could study all sorts of stuff. You could see if people will report errors to authority figures, or I mean, you could see a whole branch of research that doesn't have to just be electrophysiology. That
Like,
benefit from that.
as because of the conduit, like, does this harm the participant? Is that when they're like, okay, now you can do this?
Pretty much, yeah. I mean, again, don't want to spend too much time talking about IRB, but their whole job is to assess the risk of your experiment, and if it's deemed too dangerous, then you just can't run it. But people can do a lot of stuff. It's just nowadays it's a lot more controlled than it was in like the 60s, 70s, 80s, when people were doing all sorts of crazy stuff, like the Zimbardo prison study. But so another parameter of the P3, and this one is just so cool, and Marta Kutis discovered this one, is the subjective probability is important. So when there are multiple targets or non-targets, all targets will elicit a P3, and none of the non-targets will. So this is actually the example of the oddball task that we used, right? So you guys, every block, you were given 1 target letter for that block, but all of the other stimuli were non-targets. So if we were to look at the distribution within that block, it might turn out that your non-target letter was actually the most common letter that you saw, right? So you might have seen, out of all of these, in this example, you see X this many times, and every other letter, because the non-targets are sort of distributed, you actually see them way less frequently, any individual letter, than your target letter. But because they belong to the non-target class, even though they are less probable than the P300, the subjective probability of like, okay, this is my target stimulus, it gets you sort of draw this line between your target and your non-target. And actually, Marta discovered this with male and female names. You know, back then, the 80s and 70s and stuff, there was sort of like a line drawn of like, these are male names, these are female names. Obviously, there's ambiguity now, but back then it was that was like a very easy experiment you could run on people, and it showed incredible effects. Actually, experiments down that line eventually led Marta to discover the N400, which just read some of her papers to learn about that. But yeah, so those are the main parameters that I wanted to address. Do you have a question?
Yeah, I was just wondering if you could explain subjective probability.
Yeah. So I guess the way to rephrase it is it's essentially whether or not, so the global probability of the target in this case, which is our x, is higher, right? It's more probable than any of the individual non-targets, right? So there's more x's than a's, there's more x's than b's, there's more x's than c's. So like the actual global probability of your target is higher than any individual non-target. But subjectively, right, because all of these stimuli belong to this larger class, which is called non-targets, and the subject is given a specific task, which is, you're attending to target stimuli only in this case, like you're going to have some goal related to your target stimuli. The subjective probability comes into play here, that it's what's perceived as being a target versus a non-target, right? So it's like subjectively, the probability of the x is much lower than the non-targets. That's like I understand that the term is a little ambiguous, especially because subjective probability can also refer to, and I didn't want to talk about this because again the P3 is very complicated, but if the participant thinks that the target is more or less likely, that will also affect the P300 amplitude. So subjective probability can sort of refer to multiple different things, but this is like the classic example of what we're talking about. So it's essentially like the relative distribution of what the participant thinks is a non-target versus what the participant thinks is a target, regardless of what the true rates of those stimuli are.
Okay.
Yeah. I'll also highlight, because there's this great chat or a great talk that Manny Donchin had with the BCI Society. Manny Donchin was probably the most prolific P300 researcher and Marta's advisor. He gave this great talk where he said the most important thing about the P3 amplitude and whether or not you get it is the probability. So in the BCI world especially, we'd like to talk about the P3 as being elicited only by task relevant stimuli, and that's the most important thing. And we sort of depend on that for generating our P3B spellers and stuff. But in reality, and there's this great experiment from like mid 60s or early 70s, where essentially you do a classic two stimulus oddball, and you sort of titrate the rates, right? So it's like first you have it so that the target is 90% improbable, or sorry, yeah, the target is going to show 10% of the time, non-target 90% of the time, and then you go target, 80, non-target 20, target 70, target 60, target 50. At target 50, your stimuli are just as equal, but the task relevance is coming into play, so you will see a larger P300 for the target than the non-target, but then they keep going. So then they make the target 40%, target 30%, target 20%, target 10%. And at that point, the non-target has a larger P300 response than the target. So even though they still have the same task, and that task relevant portion is still like, count how many times you hear or see your target, but ignore the non-targets. Even though that task stays the same, the probability determines like which P300 amplitude is going to be larger. So that's sort of why I'm highlighting probability as being so important in these different types of probability. It's like the most important factor of P300 amplitude, not whether or not it's task relevant or anything else like that, although that is also important. Again, very nuanced. Yeah.
Sounds like we're making kind of like a categorical decision. Is there some components that come that shows that we're making this, let's say, target, we categorize that as a target, and then as the percentage changes, we categorize it as non-target. Like,
yep.
This, or it's just P3 doing stuff.
It's a very complicated question. I mean, it's a really, really beautiful question. But so yeah, I mean, this distinction is what we're calling a target or a non-target is very task dependent and experiment dependent, and the processes that are elicited by these task constraints are also very task and experimental, related. again, there's an entire family of P300s. We know for sure there's at least the P3A and the P3B, but like some people think there's multiple types of P3Bs, some people think there's multiple types of P3As, and there's tons of other components that seem to be P300 likes and are modulated by similar but not the same parameters and task constraints. But also, with all of these later cognitive potentials, like anything after 200 milliseconds, 250 milliseconds, there's almost certainly an overlap of multiple components happening at that same time. So like it can be difficult to design tasks that are just eliciting a P3B but not an N400, for example, because of, if you have task constraints, then you usually have some sort of semantic or syntactical constraints related to that task and task learning. So it's hard to say for sure that it is like just the P300 that's being influenced in that case. But people have run, the way that we sort of get to that is people replicating these experiments and running variations where you start to control for, certain conditions that allow you to say, okay, I'm pretty sure this is the P3 that's changing and not, the N4 or some like whatever later cognitive. You know what I mean? But it's always good to have in the back of your mind is this the actual thing that's being modulated by this effect, or are we seeing some downstream events of some other processes? And that question can be incredibly difficult to impossible, well, with our current tools to answer sometimes. But again, luckily the P3 has been studied extensively and uniformly since, the 60s and or 2023 now. So there's a lot of literature on it. As an aside, I was writing this conference paper for CogSci a few years ago, and I thought I discovered something new with the P300. My task was very weird, and it was an analysis I was not planning on doing when I designed the experiment, but like COVID happened, and I just had to do something, and I started asking questions about my data that I just would not have asked otherwise, and I found something really cool, and I was like, oh shit, like is this new, or is this something that people have discovered before? And I asked Marta because, she was doing this research and knew all those people, and she's like, I'm not sure. Do a literature review and then like write a paragraph, and I'll send it to like all these P300 researchers, and I can ask them. But before that, I went and I did this insane deep dive, and I read like over 100 papers, like just from like 1965 to like 1990 on the P300, just looking for this effect, and it didn't seem like anybody else had found it before, but the amount of information on this component is absolutely insane. I was looking for one very specific thing, and I easily found 100 papers. Like, it's crazy. And that's not even including all of the BCI papers that use P300s, which is like, at least half of the BCIs, I would imagine.